Moving on to the next enzyme that's different in gluconeogenesis. So this is not the next step, but this is the next one that is different between gluconeogenesis and glycolysis. This is fructose 1,6-bisphosphatase. This is the reaction the enzyme that replaces phosphofructokinase. As you'll remember, phosphofructokinase had a lot of regulation involved in it, and so does fructose 1,6-bisphosphatase. As far as this reaction goes, this is going to take fructose 1,6-bisphosphate and hydrolyze the phosphate group off of it to make fructose 6-phosphate, an inorganic phosphate. Having that hydrolysis is thermodynamically favorable all by itself, and so that is going to be the driving force of the reaction and will yield that negative delta G value. This enzyme is going to be activated by citrate, which inhibits phosphofructokinase, and inhibited by fructose 2,6-bisphosphate and AMP, both of which activate phosphofructokinase. So there's those three molecules: citrate, which activates this enzyme, fructose 1,6-bisphosphatase, and then fructose 1,6-bisphosphatase is inhibited by fructose 2,6-bisphosphate and AMP. So those three molecules play a key role in regulating which enzyme is active, fructose 1,6-bisphosphatase or phosphofructokinase in glycolysis. So this is what we call that reciprocal regulation between glycolysis and gluconeogenesis, where you have that opposite regulation between those two enzymes. And this regulation is what we're going to be talking more about in this video. What you see here on the far left is looking at increasing concentrations of fructose 2,6-bisphosphate by itself, and looking that the more of that you add, the lower the activity. Then if you have a case where you've added that fructose 2,6-bisphosphate as well as AMP, you see that these things then go together and you get even greater inhibition. Finally, that last one, looking just at fructose 2,6-bisphosphate and at relative activity. Again, the more of that you add, the lower things go. So this is just to show that those inhibitory effects of fructose 2,6-bisphosphate and AMP are separate. So they both inhibit fructose 1,6-bisphosphate, and since they both inhibit this enzyme, when you have both of them together, you get greater inhibition. What we're looking at, what the purpose of this slide is to talk about the enzymes that are going to either create or break down fructose 2,6-bisphosphate. So the previous slide was talking about how fructose 2,6-bisphosphate was this great thing for regulation. It's going to inhibit fructose 1,6-bisphosphatase. It's going to activate phosphofructokinase. So fructose 2,6-bisphosphate, that sugar, is an important inhibitory molecule for fructose 1,6-bisphosphate, an important activator for phosphofructokinase. So how much of that we have is important. So what this is trying to look at is how you can make fructose 2,6-bisphosphate or how you can get rid of it. So either you're going to have a kinase, which can put on that phosphate, or a phosphatase, which will remove the phosphate. So the kinase reaction is on the left, the phosphatase reaction is on the right. The reason why you have this giant pink bar in the middle is that this is one enzyme that will do these functionalities. So you have one whole enzyme that has these two opposite functions. So there's one enzyme that has both a kinase activity and a phosphatase activity. Since one enzyme has both functions, there needs to be a way to guide this enzyme as far as which way is it going. Is this enzyme going to be in the kinase mode, adding phosphates to fructose 6-phosphate, creating more of that fructose 2,6-bisphosphate, or is it going to be in the other mode where it is removing phosphate and where it's taking the fructose 2,6-bisphosphate and removing a phosphate to go back to fructose 6-phosphate? In order to control that, glucagon, a signal that says that the body is low on glucose, will then activate a variety of other kinases, which will then phosphorylate this enzyme. So yes, you've got phosphates running rampant throughout this thing. So when glucagon activates that kinase reaction and this enzyme is phosphorylated, that's when we're going to have the phosphatase activity. And we're going to be breaking down that fructose 2,6 bisphosphate. That should make sense since the fructose 2,6 bisphosphate inhibits gluconeogenesis. If we're talking about we're in a low sugar situation, it's possible that the body actually needs glucose either for the brain or for the muscles. And so if we're in a low sugar environment, then what we likely want to be doing is helping create or make more sugar, or at least not breaking any more of it down. So again, remembering that fructose 2,6 bisphosphate will activate glycolysis, but if we're in a low sugar environment, we likely want to stop breaking down the sugar that we have. And so that's going to act then. So glucagon then will phosphorylate this enzyme, which will have it basically focused on saving the sugar that it's got. The last part of this here is looking at the fact that fructose 6-phosphate actually naturally does a negative feedback loop on the phosphatase activity. So if there is a lot of fructose 6-phosphate hanging around, then it will go ahead and block the phosphatase activity of this enzyme. This is trying to get a better bird's eye view of that phosphorylation happening. So focusing on the center for just a minute, what you have in the middle is, again, you have the kinase activity and the phosphatase activity in one tandem enzyme. So either this tandem enzyme can be activated where it has the kinase activity activated, or it can be where the phosphatase activity is activated. If it's phosphorylated, then the phosphatase activity is activated. Glucagon, when we have low blood sugar, is going to activate protein kinase A, which will phosphorylate this tandem enzyme, which then means that the phosphatase activity is active. As we continue looking at the blue arrows and continue then looking to the right, that then is going to mean that then gluconeogenesis is more active. So glucagon is going to phosphorylate this tandem enzyme so that gluconeogenesis is more active, which will then have a smaller supply of that fructose 2,6 bisphosphate, greater supply of fructose 6-phosphate. So glucagon is going to have gluconeogenesis be more active. Insulin, on the other hand, is going to stimulate protein phosphatase 1, but the important part here is, again, it's a phosphatase. So insulin is going to remove the phosphate from that tandem enzyme, which then is going to allow the kinase activity to be activated. So removing the phosphate is going to allow the kinase activity to be activated. Once the kinase activity is activated, that's going to stimulate that production of fructose 2,6 bisphosphate. Fructose 2 bisphosphate is going to activate phosphofructokinase, inhibit gluconeogenesis, and stimulate glycolysis. So again, we're going to see that insulin, when you've got a lot of blood sugar, is then going to be stimulating the glycolytic pathway. We have too much sugar, we're going to start breaking it down. Glucagon is going to do we don't have enough sugar, so we need to stop breaking it down and potentially make more. What I highly recommend that you do is there's a lot of arrows on the previous two slides. I highly recommend that you stop the video, take a deep breath, and look back and redraw this stuff out so that you can describe what happens with glucagon and what happens with insulin. Because all of those are sugar controls, and gluconeogenesis and glycolysis are all about sugar.